Now we will be examining the first order circuits mathematical model, this model called state equation. So let's examine it step by step. Just a moment. Resistive circuits mathematical model was linear algebraic equations. These are the equations that we have seen already. Linear algebra we have used, and we have solved these equations in order to analyze a resistive circuit. Energy stored L and C elements included circuit's mathematical model is ordinary differential equations. Why it is ordinary, I am going to explain. These are called state equations. So this is an ordinary differential equation represent a physical system. We give a special name for this differential equation because it represents a physical system. We call this state equation. Mathematicians, they don't use that name, but in circuit theory we do use this is the physical system. In circuit theory we call it state equation. So let's explain the ordinary differential equation. Ordinary means one independent variable we have, that is time. If it has more than one independent variables, that could happen in electromagnetic field theory. You're going to see this in another course, not in this course. If it is 4 independent variables, then differential equations are going to be partial differential equations. This is another mathematical subject that you could learn, you're going to learn. In here, we have not partial differential equations. Since the independent variable is just one, it is ordinary differential equations. We call it ordinary. In Turkish, we call it adi diferansiyel denklemler. So in this equation, in this differential equation, we are going to see the derivative. That note shows the derivative of the unknown itself. These are the known functions. A and B's are the coefficients. Let's go a bit more detail of this differential equation and meaning all the elements within this differential equation. T, independent variable, I already explained. In mathematics, normally we use that, instead of the T, we use X as an unknown. In here, this is T. Okay. And xt in this equation, in this state equation, xt is unknown. It is a column matrix. If it is not first order but higher order, then this becomes a column matrix. In this column matrix, we have unknowns. These unknowns for these state equations has got a special name. We call them state variables. These state variables in our course are going to be capacitor voltages and inductor currents. So state variables would be those two. There is no any other state variable. So in the state equations we are going to see only the state variables, and the state variables are going to be inductor currents and capacitor voltages. For example, it cannot be capacitor current or inductor voltage, the other variables that we're going to use. In first order circuit, there is only one state variable. So if you are talking about the first order circuits, for example, these are the first order, one inductor included here. So for this circuit, the state variable is going to be inductor current. For this circuit, it's going to be capacitor voltage. This A, it says capital A here, but inner A, A is, if it is a constant, this is a first order circuit related differential equation. If it is higher order circuit, then A becomes a matrix, square matrix. What is inside this square matrix elements are the parameters that we see in the definition relations of the elements. In first order circuit A matrix, if the circuit is first order, the A matrix becomes a constant A. B is a column matrix in general. It has got constants. These constants are the parameters that we see the definition relation of the elements. And this UT is the independent sources related variable. That means if it is independent voltage source, voltage we're going to see it. If it is independent current source in the circuit, then independent current source current will be seen there. There could be more than one voltage independent voltage source and independent current source. For those we are saying whatever known in the definition relation for these independent sources, these functions are going to be the same here. So these functions are known functions. And it says it could be a DC AC sources, no limit on that. And UT, that is it. First one usually there is one function like that. Okay. So it says here, once the state variables are found, then all the elements, current and voltages will be found. So as soon as you see that equation here, this unknown is, we already said the if it is the first order inductor current, so you're going to find only one variable within your circuit. What we are saying, once you have found these state variables, you can find all the elements, current and voltages by using this state variable that you already found. So it is like mesh current method. First we calculate the mesh currents. Once we calculated the mesh currents, we can find all the elements, current and voltages. It is like that. Once you have calculated the state variables, then you can calculate all the elements, current and voltages. We are going to see it later on. Now we just explained what this state equation is. The next step is how we are going to find that. In general, finding state equation in circuit theory requires graph theory, which is not part of this course. Therefore, since circuits, first, second order circuits are simple circuits, state equations will be found by a reasonable usage of RL, RVL, ICL equations and the element definition relations for the given circuit. So as we said, in general, classical methods write all the independent Kirchhoff voltage law equations, Kirchhoff current law equations, independent ones, and the definition relations. We are saying if the circuits are simple, so simple means less number of elements in it, so these equations are not that high, so we could write these equations. From these equations, by reasoning, we are going to end up with first order differential equations. I am going to show it how you could do it for the first order and second order circuits. In an example, I'm going to show it. But what happens, we are going to do all this by hand, but if the circuits are more complex circuit, means there are many elements included in it, and higher order differential equations required circuits. That means many inductors in it, many capacitors in it, then it becomes a complex circuit. How we are going to analyze this circuit, because we are saying not these numbers of equations that we are going to write is going to increase, and differential equations, many state variables are going to be seen in. So we are going to use the Proteus simulation program for that. This program does it for us. It does it by solving the differential equations. So this calculations, which is boring and takes quite a long time if you do it by hand, but Proteus as a tool does it automatically. Then you might say that why we are explaining the first order, second order then. In the first order and second order, the terms that we are going to use will be repeated in Proteus. All difference is the number of these concepts. Okay. What I mean by that, in the first order, you're going to have one unknown, one state variable. If it is n order equation, it's going to be n unknowns. So basically what you do in simple circuit is going to be the same as the complex circuits. So one of them is time consuming, the other one is short. So let's do an example, make it more clear to you. Here you are. We have a first order circuit here. Why it is first order? There is one inductor in it and serially connected. So we can write the KVL equations. So that means voltage of resistor plus the voltage of inductor gives you the voltage of independent source. Why it is on the left hand side, you know that. Kirchhoff current law, these are serially connected, so the current of the resistor is the same as the current of inductor, so these currents are the same. And independent voltage source current is negative to this one. Why is that? Because according to passive sign convention, the current reference is downwards. So current reference in here, if we assume this one, is both of them coming out of the node. So one of the current is negative sign, the other current. So this is what I said. So this is definition relation of the inductor. We wrote KVL, KCL, and the KCL equations, and the definition relations for the inductor, and the definition relation for the resistor is V equal R times I, not written here, but you know that. So our aim to find this differential equation like that for this circuit, that means the mathematical model. How I am going to do it is easy. In the mathematical model, I need that independent source, because every element's current and voltages depends on that. So it must be seen in the equation. So therefore, I am going to choose this equation as my main equation. From this equation, I am going to end up with this equation. Why is that? Because VST is not seen in any other equations that I wrote here. So I will be using this one. So VST already been here, so I have found part of it directly. The other variables that I see here are not the ones that I would like to see in the differential equation. Because since there is one inductor in here, my state variable is inductor current. So I've got to transfer these voltages to inductor current somehow. If I could do so, I will end up with a differential equation like that. How I am going to do it? If you replace that VLT, use the definition relation, this voltage transfers to the inductor current. So you can replace that VLT with L DIL over dt. And for the VR, if I use the definition relation, R times resistor current, I know the resistor current is equal to the inductor current. I show them as I. Then it becomes R times I gives you the resistor voltage. So I replace the resistor voltage with that Ri and replace VLT with this term. So if you look at this equation now, if you leave the left hand side only the derivative of ILT, then it becomes this. So this differential equation is in this format. The unknown's derivative, unknown is ILT, which is IT in this case. So that is the derivative of it, left hand side. Right hand side, the coefficient of the unknown function is A is minus R over L. So as I said already, A includes the parameters that we see in the definition relation of the elements, so we have seen it now. So if you look at the last term here is B, once again equal 1 over L, that is the parameter of an element, and UT is independent voltage source. So this is now our state equation, and our state variable is inductor current. Once we solve that equation, we are going to find the inductor current. Once we found the inductor current, then I can find the inductor voltage by using the definition relation. Since the inductor current equals the resistor current, I can say that what resistor current is, and multiply this resistor current with the 1K, I get the resistance voltage, and this independent current source current is equal the negative of the resistor current. So I found the independent voltage source current as well. That means I have found all the elements current and voltages. This is what we already said, and we have done it on this example now. In here it says capacitor included first order circuit is chosen as an assignment circuit. So we have done a first order circuit analysis by using state equations in here. So you could do it a capacitor included first order circuit analysis. You do it your own at home. That is the end of this video then. Let's stop at